So, today we are going to speak about the Fridtjohn necessary conditions or the John multiplier rule, and from where we will deduce the Kuhn-Tucker conditions, but as we will show gradually with examples that in most cases the John multiplier rule gives us what we really require. So, the multiplier rule John established in 1948 was for inequality constraints, because as I told you that earlier the Lagrange multiplier rule dealt with equality constraints, though its validity was not established till late till in the 60s, but here Fridtjohn studied a problem of this form. We will show that in most cases we will get what we want. So, I will just write down the Fridtjohn condition and then try to explain to you the geometry associated with the constraints and what those things mean. So, this is a theorem. Now, observe one thing, let us assume that all of these are differentiable functions, just differentiable functions. If we have more equality constraints, we have to assume something more, that is continuous differentiability, but if you just have this, you will have differentiable functions, and we will see why it is so. So, let us call this problem as MP, math programming problem. Let f and gi's be differentiable maybe I should write on the other side of the board to have space. Let x bar be a minimum, rather a local minimum, that is a much better statement rather than just telling minimum. Is a local minimum of MP. Then there exists lambda naught greater than equal to 0, lambda 1 greater than equal to 0, lambda m greater than equal to 0, such that lambda naught, lambda 1, lambda m, this is not a 0 vector, and lambda naught 0 is equal to so here you go. The second condition is called the complementary slackness condition. Condition number 2 is called the complementary slackness condition. in the sense that both these lambda i's and gi's cannot hold with strict inequality at the same time. That is, if gix is strictly less than 0 and lambda I is strictly greater than 0, then their product would be strictly less than 0. That cannot happen. If lambda I is strictly greater than 0, then either gix star is equal to 0. If lambda I is strictly greater than 0, then gix star must be equal to 0. If lambda is equal to 0, then gix star could be strictly less than 0, could be equal to 0, but if gix star is strictly less than 0, then lambda I must be equal to 0. So, that gives rise to what is called a set of active constraints. Of course, we will start doing the proof of this, but let us go a bit to the geometry. So, these are the points where these are the indices for which the lambda i's need not be 0, may be 0, may not be. So, if all these lambda i's are 0, then lambda naught cannot be 0. Now, a very important fact here is this fact, that this multiplier is not equal to 0. If we allow them all of them to be equal to 0, then every feasible point will satisfy the John conditions. The fundamental and the crucial fact of the John condition is this. From the modern terminology, from the basis of from the modern way of talking about things, if there exists lambda naught, lambda 1, lambda m not equal to 0 with lambda naught greater than 0, we say that this thing is called the Lagrange multiplier, or we in this case are calling it John multipliers. So, we say that the John multiplier is normal. If no such lambda naught, if no such vector no such vector of this form not equal to 0 exists with lambda naught greater than 0, then we say that the only possible multiplier is an abnormal multiplier. That is, if the only set of multipliers lambda naught, lambda 1, lambda m not equal to 0, which for which 1 and 2 hold, 1 and 2 hold has lambda not equal to 0, then we say that the problem only has abnormal multipliers, and the problem has abnormal multipliers. Or the good case and the bad case. The good case is that it is enough just to have one such multiplier with lambda naught strictly greater than 0, and the bad case is that you do not have any multipliers for which lambda naught, which satisfies these two, and for which lambda naught is strictly greater than 0. And it looks that okay, why are you bothered with lambda naught equal to 0 and lambda naught strictly greater than 0? When we have lambda naught strictly greater than 0, you can just write lambda naught equal to 1. So, I am bothered because if lambda naught is equal to 0, then grad f x would have no role. But the important part is that in most examples which we will start learning maybe from the next lecture, you will not have lambda naught 0 except for pathological cases. This abnormality, abnormal normal case implies normal multipliers. Pathological case abnormal multipliers. Now, let us do the let us look at it geometrically. What is the normal case and good case and what is the bad case? So, here I would just rub this part which you have already seen, or you can roll back the film and see it again. So, G1, suppose I have two constants G1 and G2, and so here is G1 x. So, this is the curve giving me G1 x equal to 0. So, I am in 2 dimensions. So, there is another curve giving me G2 equal to 0. So, this is G2 and this is my common zone. So, this shaded region is my feasible set G1 x less than equal to 0, G2 x less than equal to 0. Now, suppose this is the point where I am interested in looking into the nature of the behavior of the gradient of this and this, because for example, this could be my solution point. Let me assume that there is this is my solution point. Now, at this point, whether I have the good case or the bad case, that is what we have to really decide. If you look at G2, this is the surface of G2 and then you really have to have the normal, it has to be perpendicular from the surface. So, at this point x bar, this is my grad G2 x bar, and at this point if I look at G1, this is my grad G2 x bar. So, you observe that these two are linearly independent, and now assume that here is the unconstant minima and here is the level curves. Level curves means the set of all x if I take the minimum f x such that f x equal to some alpha. So, alpha is 0 and then, so but this is a unconstant minima. So, if so from unconstant minima I am just trying to, so basically it is some circular function, a nice convex function, basically a paraboloid. It is coming like this, it is coming like here. And there is the level curve, and there at this point the gradient of f on this level curve where it is touching and where the optima is achieved on that level curve, this would be my grad of f x, because it is perpendicular to the surface of the level curve. Now, you see how can I represent grad f in terms of this? I can always write that grad of f x bar. So, if I take lambda, say positive non-negative lambda, lambda 1 and lambda 1 and lambda 2 and add them, let me see, lambda 1 grad g 1 x bar plus lambda 2 grad g 2 x bar Now, because I have taken a positive multiplication, it will remain on this side and this will be my final linear combination for example. But then this linear combination here is exactly opposite to grad f x. So, minus of grad f x can be represented like this. So, I can write instead like this, grad f x is this. So, finally, I will get and this is exactly the first equation of the John multiplier rule. So, here you see they have a nice behavior. Here you see I have got a regular, I have got a normal multiplier. I have shown that this lambda naught is greater than 0. So, this thing if you observe comes very naturally from the equation itself, because if you are having this scenario, now you have this scenario. Now, if lambda naught is equal to 0, it would imply that and because I have to, because these are the multipliers which are satisfying the John rule, then and because lambda naught is 0, then lambda 1 to lambda m, this vector, because lambda naught and lambda 1 lambda m all are 0, cannot be 0. So, among these one of them has to be non-zero. So, this vector itself has to be non-zero, which is implying that grad g1 to grad gm, this set of vectors is linearly dependent. Which is implying that this set of vectors grad g1 at x bar to grad gm at x bar is linearly dependent. Now, what does it mean? If lambda naught is equal to 0, these vectors are linearly dependent. So, if these vectors are linearly independent, these vectors calculated at x bar, the grad g1, g2, gm, then lambda naught is not equal to 0. P implies q, negation of q implies negation of p, very simple fact of logic. So, if this equal to 0, these are linearly dependent of, but if these are linearly independent, this cannot be 0. So, which means a natural assumption that one can impose on the constraints is that all these things cannot be, these vectors are all linearly independent. Of course, when you take linearly independent, you have to take m less than equal to n, because the maximum number of linearly independent vectors in Rn is of course just n. So, if from the condition itself that what would an abnormal multiplier give me, that leads to a way by which we can guarantee that the multiplier is normal. So, this is an assumption on the constraint, which is usually referred to as a constraint qualification. Constraint qualification. That if you say that this is linearly independent, of course, this assumption would immediately imply that m is less than equal to n is linearly independent whenever you may impose this, that this is linearly independent, then lambda naught is strictly greater than 0, that is the multiplier is normal. This fact is amply shown here in the picture, because here you see in a 2-dimensional setup, if the angle between two vectors are either 0 or 180 degree, then the vectors are linearly dependent. Here they are not, the angle is an acute angle. So, thus these two are linearly independent vectors, guaranteeing that what we have is a normal multiplier. Okay. Now, let us see what is the situation where we can have only abnormal multipliers. There is no way we can get a normal multiplier. So, here I am just rubbing this part off, maybe here. Now, let us look at this situation. One thing says y is greater than equal to x square, another thing says that y is less than equal to minus x square, some sort of thing like this. These are R2, right, and so this will give rise to x square minus y less than 0, and this will give rise to y plus x square less than equal to 0, and only possible solution to these are, this is just the point 0 0. This is a typical situation where a linear independence usually fails when you just have one element in the, not always, but one of the cases where linear independence have a high chance of, linear independence have a high chance of failing, because if this is my G1 and this is my G2, then this is what I have as and this is what I have as so these are the pathological cases where linear independence is failing and can lead to non-regular multipliers. We will give a more detailed example after we prove the multiplier rule, because it needs a lot of things to be done before a multiplier rule can be proved even just for inequality constraints. Then we will give a concrete example where showing, and that example is due to Kuhn and Tucker in 1951 paper, showing that the only possible solution of the set of Lagrange multipliers, the only possible Lagrange multipliers that will satisfy is the one with lambda not equal to 0. So, that would be very important. Here you can see that grad G1 and grad G2 are linearly dependent. And see what would happen in this situation, because you can always write lambda 1 as minus lambda G2. So, lambda G1 x bar is equal to minus lambda or lambda g1 x bar is equal to minus lambda g2 x bar. I say lambda is greater than or equal to 0. So, you have g1 x bar plus lambda grad g2 x bar is equal to 0. So, in that case it will really depend on the objective function. You can always, of course, you can always prove that there can be a multiplier with lambda not equal to 0. If particularly put lambda not equal to 0, the inequality is still holding, does not matter. But it does not mean that lambda not only would be equal to 0. There is not a there cannot be a set of multipliers on G1, G2 where lambda naught actually is still non-zero. So, that is the thing that we are trying to figure out. We are trying to say that these are the cases where there are high chance of generating multipliers which are abnormal. See, what constraint qualification does is that it tells you that the multiplier can never be abnormal. So, once you, but in the pathological situation the thing is much more interesting, I would say, in some sense, that in the pathological situation it is very difficult to say whether the multipliers would be normal or abnormal. Of course, in some cases one can show that okay, the only possible multipliers are the abnormal multipliers, they are very bad problems actually. And in some cases, even if all these regularity that you are imposing on the constraints do not hold, still the multiplier can be regular. And that is a crux, that this whole story of regularity on that is imposed on the constraints, which leads to what is called the Kuntaker condition or the constraint qualifications. One need not always worry about that, because in many situations, even in pathological cases, which is coming out in latest last in current research also, that even in pathological cases you have lambda naught strictly greater than 0, and in fact in many situations the problem, the condition of the problem itself guides you to show that the lambda naught would be anywhere greater than or equal to 0. So, if you can just find a set of regular multipliers, then it is alright. The bad cases are where you cannot find it as a regular multiplier. You cannot find you cannot find a not regular, find a normal multiplier. So, let us try to prove what we have mentioned. So, what we are going to prove from the, how are we going to prove the John multiplier rule? What is the meaning of a solution even locally? So, for x very near x bar, for which this is true and this is true, this is your local minimum for x near x bar. You can understand x very near x means we are talking about a neighborhood and all those points. Now, from here what can I say? So, x is very near x bar, then I can replace f x with its linear approximation, that is, instead of f x I will write down its linear approximation around x star. That linear approximation of a function around a given point x star is sorry f x minus x star. So, if instead of x a point which is nearby, I can write as lambda d for some given direction d, x plus lambda d, x star plus lambda d. So, x can be written like this for lambda very small, lambda greater than 0 very small. I think I should write sufficiently small, but okay, just I am writing loosely, sorry, in Gx less than equal to 0. This is the meaning of local optimality. Now, I want to replace fx here by, because x is very near x star, we can replace the function by its linear approximation, that is the first order approximation of f around x star. Basically, you write the Taylor's expansion and ignore the remainder term, that is the idea. That is the model. So, you are replacing the original function which could be nonlinear by a linear function. For example, sin x is replaced by x. For example, those who have forgotten this basic fact, when we look at the sin x graph. So, very near x, when x is very near x, its difference with the line y equal to x is very less, but as you go out, if you go more towards this side away from 0, the difference starts increasing. But as you come very near 0, that is why you have learned in say in physics that they always use sin x is almost x when x is very small. So, the same idea is being used here. So, what we get here is now Gx star plus lambda d, sorry, I made a mistake, Gx should be less than equal to 0, x should be feasible. Please just correct this mistake. It should be that Gx bar plus lambda d should be less than equal to 0. So, I am just finding one of the x's. So, one x could be like this, a point which is very near x and is feasible means this and is also satisfying this. So, when lambda you take any x d, so if you are not still comfortable with the geometry, suppose this is your x. So, what I do is a local minima means that if I take a ball around this and then look at the intersection of the ball with the set and see, and at this function point is a minimum for all these points here. Now, what I do if I take this as point as x bar and I take any direction d, then I take x bar plus lambda d, which should be like this, x bar plus lambda d, this is some lambda d, this is x bar, lambda d is something, maybe this is d and this is lambda d. So, this is x bar plus lambda d, but this x bar plus lambda d is outside this particular set, right. So, here you keep on shrinking, you can come here, but you can never come very near. You can come very near to x bar, but you are not still inside here. So, that sort of d I do not want. I want a d, for example, if I take a d like this, that sort of a d also will not give you anything. So, I need a d where I make this sum. So, if I take a lambda, if I take a proper lambda or proper length, I can actually move along this and come to this point. So, that is why this condition has been written. So, now I am replacing it by its first order approximation, which is fx star plus lambda minus fx star and here I also write the first order. I am just taking 1 g. So, let me just gi okay fine. So, for each gi I write gi x star plus lambda so it cancels. So, basically I will have there is a lot of deep geometry involved here, but okay. What I am trying to show here is the following, that if optimality occurs, then this sort of there must be a D which has to solve this. So, which means if you look at this, if there is a D for which this is strictly less than 0 and this is less than equal to 0, which means there is a feasible point from where I can actually make a better move, I can decrease the value of f. So, I have not reached the optimal. So, if I have reached the optimal, so I will get something like this. So, which means that this strictly less than 0 cannot occur, and as we will observe we will show that these two equations cannot occur, this system cannot have a solution. So, if x star is the local minima of the original math programming problem, and this system where I is belonging to I x bar, this system cannot have a solution. If you are uncomfortable with I x bar, we can still make it much more easy looking. So, I can say that this system, actually this is much more, and this system and this is for I equal to 1 to m. This system has no solution, because if I take I equal to I x bar, that is g I x star is 0, I x star I guess. Okay. So, because I am giving x star because x star was the symbol I had given in the main result. So, here if I take I x star is equal to 0, because if I x star is strictly less than 0, then it is quite simple to do that, because if g I x star is strictly less than 0 and this is strictly less than 0, then both of them are strictly less than 0 if there is such a D which satisfies this. But if g I x star is equal to 0, then I can just put here as put the g I x star equal to 0 and get just this part. So, this system does not have a solution. This is what we need to show. And here we gradually get into the more deeper depths of convexity, and we have to talk about separation theorems and all those stuff. So, let me tell you one thing, tomorrow we will start by proving this. Now, after I prove this, you might ask me, okay, how do this is such a difficult thing, how can I show that a system is inconsistent? It is not so easy to show that a system is inconsistent, possibly it is easier to solve a system rather than showing a system is inconsistent. So, we will first show that if this system is inconsistent, what is consistent? is there anything consistent which you can actually compute. To do that, we will need to talk about separation theorem. So, first we will talk about this, and in order to say that if this is inconsistent, what is consistent, what is the corresponding system which is consistent. The inconsistency of this should be equivalent to the consistency of something else. So, we will show that in order to do that, we should learn about convex, of course, you know about convex sets a bit, about separation theorems and the Gordon and the theorems of the alternatives, which will finally lead to the John multiplier root. So, here we are making a step by step study, and we will start giving a lot of examples, and we will show that actually in most cases the multiplier rule gives you normal things, and we will in fact do a lot of examples in this course. Thank you very much.